So, yesterday we did our first scattering problem, okay, which was the scattering by a step. Okay, so I wrote here the energy, this is x, this is the energy, this is V0, positive. And we consider both cases. One case where the energy was less than V0, and one case where the energy was greater than V0. Okay? The difference between these two is essentially what the wave function here does. If you remember, in this case, we said take the wave function here, tk e to the iq times x, okay, with an I. So a wave that goes, a plane wave. In this case, we took the wave function very similar, but with a crucial difference, e to the minus qx, so a decaying exponential. Okay? These are physically very different, although formally it looks like you just send q to iq and you get this. Okay, so the algebra can be shortcut, but there is a very different physical meaning of this. Okay, and you understand it by calculating the current density. Okay. So here there is no vector nature, we are in one dimension. So let's write the expression for the current density. Remember, it's 1 over 2m. So the current density of a wave function, we are calling it phi k of x, okay? Where to the right I have this, and to the left I have e to the I k x plus r k e to the minus I k x. And remember that k is related to the energy in the usual way. Okay? Good. So let's calculate for this the associated current. It would be phi k star, the momentum applied to phi k, plus, in a democratic way, the momentum applied to phi k star phi k. Okay? This is the kind of easy way of remembering the stuff. Okay? Good. And remember, P over M is the velocity somehow. Okay. Now, what is P of? Let's start with this. Okay. P of phi k. Well, it is equal to minus I h bar, the derivative of this object. Okay, so the tk, you can take it here, and then when you take the derivative, you bring down minus q, and then I have e to the minus qx. Is it clear? This is P applied to phi k. Okay, good. So I write it as I h bar tk times q e to the minus qx. Okay, good. Now I multiply, and now I have to multiply here by the complex conjugate. So this object here is tk star times e to the minus qx. Okay? So let's calculate the first term. The first term is tk star e to the minus qx times I h bar tk q e to the minus qx. Okay? I'm doing just this calculation. And the result of this object is I h bar tk modulus square times q times e to the minus 2qx. Okay? And then I look at the second term. Do I need to do many calculations? It's the complex conjugate, okay? If you take the complex, so this is the complex conjugate of this, right? But here there is an I. Okay? And therefore, what do you get? 0. Okay? So the current associated, so the J here, in this case, is 0. Now, how might I conclude the same thing without even doing a calculation? I told you that the current of a real wave function, which is real disregarding the possible phase in front, because here nobody guarantees that tk is real, okay? But it doesn't matter because it's a phase, is a factor in front. The actual wave function, in fact, you see tk modulo square enters, not really the phase of tk. But the essence of the wave function is a real wave function, okay? And real wave functions do not carry momentum and do not carry current, okay? That's the point, okay? So, yes, you can calculate it, but you can also conclude that it should be 0. Fantastic. But then, we said that the, remember, the P of x and t with respect to t is equal to minus the divergence of the current, okay, on any evolving wave function. So we said for stationary states, which are the eigenfunction of the Hamiltonian, this is 0. Okay? Which means that the divergence of the current of any stationary state should be 0. But the divergence of a current in one dimension, what is it? The derivative with respect to x of j of x. Okay? So this should be 0. What means that j it must be a constant. Okay? But it is 0 here. So what should be the current here? 0. Okay? So the current on the left-hand side, in this case E less than 0, should also be 0. Shall we calculate it? Let's see if it is 0. Okay? So I do the same calculation, but now I have to remember that my wave function is slightly different. It is this, okay? So when I apply P to phi k, first of all, I have here IQ, and second, I have here IQ. Okay? So let's redo the calculation. The calculation gives me I and a minus, and the minus becomes a plus. So the I goes, and here there is a I. Okay? It's almost the same, but with a very crucial difference. The I was making things cancelling is gone off. So let's calculate now this first piece. Again, this is e to the now minus iqx. So I multiply, and then I have here no I, and here I. And let's see. Tk modulo square is there, h bar is there, q is there, but here minus and plus the other way. Okay? So this is just a number, a constant. Okay? Now let's sum with the complex conjugate. It's real. Okay? So what is the current? What is the current in this situation here? Well, it is j for x greater than 0 is equal to 1 over 2m h bar tk square q plus the same, so a factor 2. Okay? So the 2 and the 2 goes, and the result is tk modulo square times h bar q divided by m. Okay? So somehow the momentum divided by the mass times the amplitude of the wave. Is it a reasonable thing? Yes, okay? So, zero current here, in this case, Jx greater than 0, the current is not 0, and is equal to Tk modulo square times h bar q divided by the mass. Okay? So you see how big is the difference with a function that is intrinsically complex, like a plane wave. Okay? It carries momentum and it carries the current that we have just calculated. Okay? Now we have to impose that on the left is exactly the same thing. Okay? So let's calculate the current of this object. So it's slightly more complicated calculation, but not very complicated. Okay? So let's do it. I erase. When you do calculations, always try to make the algebra as clean as possible. Spend some time. Maybe you think that you are wasting time because you are slow and careful. You're not wasting. Okay? It's an investment because you make no mistakes. And if you make a small mistake, it's easy to... This is a suggestion for the midterm, the final, whatever exam. It's always the same thing. The more careful you are with your algebra and neat, the better it is.
Sorry, there should be z less than 0.
What?
X less than 0.
Where?
The thing that we calculated, pk.
Here.
Yeah.
No, this is greater than 0. I am still calculating the current here. But this is for this wave function, and this is for this. In both cases, here. So when the energy is less than 0, I have 0 current. When the energy, less than V0. When the energy is greater than V0, I have a finite current. Sorry, I have done calculations only for this x greater than 0. Now I will calculate for x less than 0, where the wave function has always this form, and this is slightly more complicated to calculate the current, but I know that the current should be imposed to be the same, because the divergence should be 0. Okay, so this is something that I will be ready to impose to my calculation. Okay, so let's calculate, as usual, P phi k. Phi k is now this, however. So this is minus I h bar, the derivative of e to the I k x plus r k e to the minus I k x. Okay? I do the algebra as if I were to do it on my midterm exams or whatever. Okay? So I just do it very, very carefully. Derivative of the first. What is it? You bring down I k. You see, I do not shortcut my steps. I square minus 1, because there is always the possibility by jumping a step that you introduce a subtle minus sign and then you are kind of lost. Okay? I k e to the I k x plus r k times minus I k e to the minus I k x. Okay? Fantastic. Good. Now I multiply this by phi k star here. Phi k star. Okay? So here I want phi k star. And here phi k star. I do this on the board. I wouldn't do it on my piece of paper, okay, because it's ugly to see those things, but this is just to tell you that here I want e to the minus I k x plus r k star e to the I k x. And this multiplies the expressions that you have there. Okay, so this is in fact a parenthesis if you want. Here, okay, so I write it as minus I h bar. Okay, now I have I k e to the I k x plus, or better, minus I k r k e to the minus I k x. Clear? Okay, now I can do several things. But first of all, if you want, okay, I times I is a minus 1, so you can rewrite, if you want, with an extra step, this as h bar k times e to the I k x, and this is a minus plus, but I square is a minus, so minus h bar k r k e to the minus ikx. Okay, intermediate algebra for this term. Okay, good. Now I have to multiply by this. So there are 4 terms. This times this, this times that, this times this times that. Okay, let's do it. Equal, equal. First with the first. The I minus and I plus cancel, and I get h bar k. Very nice. Let's do the last with the last. Again, plus and minus cancel. They give you 1. And I have minus h bar k, rk times rk star, so rk modulo square. Then I have 2 other terms. This times that, which is, you see, minus h bar k, rk times
e to the minus 2 minus
times e to the minus 2ikx. Okay, and then I have this times that, which is
plus h
plus, okay, h bar k, rk star times e to the 2ikx. Okay. Good. Very nice. There should be cancellations coming. Let's see. Oh, yes, yes, yes. This is only the first term. Careful. Okay, sorry. I was a bit. Okay, this is this term. And then there is the complex conjugate. Fantastic complex conjugate. So plus the complex conjugate. This is the same. This is the same. The complex conjugate of this is minus h bar k, rk star, e to the 2ikx. And the complex conjugate of this is plus h bar k, rk, e to the minus 2ikx. I relax now. Because this and this go away. And this also go away, while these two just sum. Okay? So the result of the two things is equal to 2h bar k times 1 minus rk modulo square. Okay? Very good. Now I divide by 2m, and the result is that the current in this region, okay, so the current for x less than 0 is h bar k over m 1 minus rk modulo square. Okay? Is it clear? Pretty similar to this. Okay? H bar times the momentum of the wave, but there are two waves, one with coefficient 1, one with coefficient rk that goes back, and so you have 1 minus the reflection coefficient squared. Okay? Fantastic. Now, let's consider the first case, E less than 0. The current should be 0 everywhere, because it's 0 to the right. And therefore, in this first case, you would conclude that rk modulo square is in fact 1. Okay? So you get a wave, you get a reflected wave whose amplitude is still 1. What changes is a possible phase. Okay? So the reflection coefficient is a complex number of modulus 1. Okay? So just some phase. Very good. In the other case, okay, what you deduce is the following. The function should be, the current should be the same, and you deduce, therefore, that h bar k over m times 1 minus rk modulus square is equal to h bar q over m times tk modulus square. Okay? Maybe you were expecting that 1 was equal to rk square plus tk square. The answer is no. Okay? The reflection and the transmission coefficient do not sum to 1. Because here somehow I have a q and here I have a k. In other words, the two energies here are different. However, if you do other problems, for instance, let's eliminate this algebra. Suppose that I give you the following problem to do. Okay? I ask you, okay, do the scattering states of a square well like this, which we will do in a second, by the way. We will do the bound states. Suppose that I ask you, do the scattering states. Okay, so here I have the same wave function here. Here I can set up the problem, see later on. But here somehow the k that I put are the same. And therefore in this case, real I have k and q equal to the same thing, and therefore you would conclude that 1 minus rk, which is the current here, should be equal to tk squared. Okay? So in other words, you would conclude this thing. Okay? So you will see later on this kind of more simple to understand thing when the scattering is from some level of energy with something in between to something else, which is in fact true even if this potential was more complicated, as long as you go from some energy to the same energy afterwards. Okay? Okay. By the way, same thing if it's a double step. So step up and step down rather than a well. Okay? Still the same thing. This scattering problem, so energy above the energy of the maximum energy of are exactly set in the same problem, in the same way. Okay? Good. Just one little note about the generality of the solution. I told you that here you do have really two degenerate solution, because if I take the star of the wave function, the star of the wave function is this. Okay, it's different function, and I can make a linear superposition of the phi k with the phi k star with arbitrary coefficient, and this still would be a solution. Okay, so I really have intrinsically two solutions that I can form. Pretty much like in the plane waves, I have e to the ikx and e to the minus ikx. They bring current and momentum in the opposite direction, but they are totally degenerate in energy. Okay? Here, if I take the star of the wave function, since the wave function is real up to a possible coefficient here, I do not obtain a linearly independent solution. Remember what we said. You can always change a wave function by an overall sign or an overall phase in front. This is not a different wave function. Remember for the sine function in the infinite square wave. It's the same thing. So here I have only one solution. Only. While here I have two independent solutions. Okay? Right? Good. So let's move now to a more complicated bound state. We saw the easiest bound state problem, infinite square well. The easiest scattering problem, the step. Now we move to do some more gymnastic and do more complicated problems. Let's see. Suppose that I give you a finite symmetric square well. In fact, this I am erasing, but I want to draw it here more carefully. Okay. So the potential that I imagine is this, x. I put the origin in the middle, okay? I call this A and this minus A. In the notation that we had last time, there was L to be the total width of the thing, so this would be, say, L over 2, okay? If you want to make a transcription of the thing. But the potential here is V0, okay? So the infinite square well is obtained when you send V0 to infinity, okay? Now this is finite. It's a finite square well. By the way, finite is symmetric because you could think of wells, okay, which are not exactly symmetric. It would be more complicated to do it, okay? So we do this, which is, I mean, you can make an infinite number of variations of step-like potential. You can solve all of them in basically the same way. So gluing together plane wave solutions, imposing continuity and derivative of continuity of the derivative. But the algebra to actually obtain the state is increasingly more complicated. Okay, so let's try to solve this problem. And again, there are two possible values of the energy. One is when the energy is less than V0. Okay, the energy cannot be below 0, by the way, because the minimum of the potential is 0. Okay, so I start looking, energy could be here, so greater than 0, but less than V0, or second possibility, energy greater than V0. Okay? Well, you realize that A greater than V0, you will not find bound state, but you can find scattering solutions. Okay? Slightly more complicated than the problem we did, but not infinitely much complicated. Let's look at the bound state problem, okay, which we did for the infinite well. Now, there should be precise energy eigenvalues here, one or more, inside the well, so below the thing, for which there should be bound and normalizable states wave functions, okay, which we want to calculate. Now, let me start writing possible wave functions for this problem. Okay, so I have here the region x less or equal to minus a, the region x greater or equal to a, so the first region, third region, and the region in between, which is the one for x less than a greater than minus a. Okay? Region 1, 2, and 3. 1, 2, and 3. Okay? Let me start writing a possible solution inside here. Suppose that I have some energy E. Okay? Here. What would be your candidate solution? This is a free particle in a region of space. Okay, so not sine. Why sine? Sine or cosine. So let's be general. So I call B e to the I kx plus C e to the minus I kx. In this way, depending on B and C, I could have sine, cosine, depending if they're even or odd. Okay, we can make both. Fantastic. All right. What about the solution here? So in the region 3, what was suggested?
IKX.
Yeah, not K. Remember, Q.
Yeah, Q.
Q. Okay. So D e to the minus QX. Okay. Good. Where Q has the usual relationship, which we wrote last time. Okay.
Are we calculating only the bound states?
What?
We are calculating only the
Bound states. Yes, bound states. So they decrease. Later on we'll do the, well, in fact you will do as an exercise the scattering states. Okay, good. What about this region here? Well, again, a decaying function, so A e to the qx. Notice with the plus here, if you go to minus infinity, you just go to 0. Fantastic. So I have 4 unknown 4 unknown constants, right? In fact, 5 unknown things. The energy and 1, 2, 3, 4 things. I have to find all of them. And so you might say, okay, yes, I can impose continuity here for the function and the derivative, two conditions. Continuity here for the function and the derivative are the two conditions, so 4 total. And then the normalization of the wave function. 5. 5 constants, 5 conditions. All right. But you are ready to solve a linear problem for 5 coefficients. So, well, it's not difficult, but it's a kind of annoying, very annoying. And now we use symmetry, and we will explain the general theory later on. But we understand that somehow the potential is symmetric, is even, right? So V of minus x is equal to V of plus x. Okay? So it admits parity as a good symmetry. The kinetic energy is also even under parity because it's momentum squared. So it's a derivative square. So it doesn't matter if you change x into minus x. In other words, the Hamiltonian is a parity symmetry. We'll see again the theory later on. For the time being, I want to illustrate how using symmetry we save work. Okay? Because we say, okay, the Hamiltonian is symmetric under parity. So what about its eigenstates? Symmetric under parity, but what symmetry?
Odd and even.
Odd and even, that's the crucial thing, because you might be naively tempted to say, I have to impose that the eigenfunctions of the Hamiltonian are even. No, I have to impose that they are symmetric under parity. But what sign they get when you change x into minus x, it's up to you. And in fact, they can get even functions with the plus. So an even function, if I apply, say, the parity operator, parity will be, so this is not the momentum, right? It's the parity. We will see later on. The parity operator is defined in the following way. Takes a function and it changes the sign of the thing, okay? So if I have an even function and I apply the parity operator, I obtain phi even of minus x. But even functions are just insensitive to the sign, okay? So even functions are eigenvalues, eigenvectors of the parity operator with eigenvalue plus 1. On the contrary, if I have an odd function, okay, so the definition is that you have to take the odd function at position minus x. But the odd functions pay a minus sign to become the same function at x, okay? So you see that this is an eigenfunction of the parity operator with eigenvalue minus 1. Okay? So they are both somehow eigenfunctions of the parity, but with different parity eigenvalue, plus 1 or minus 1. Both are good. Do not eliminate these poor guys simply because they have a minus sign. Okay? They satisfy the fact of being still good eigenfunction of the symmetry of the problem. Okay? So later on we will explore this theory more. But now, using the fact that the eigenfunctions can be classified according to being even or odd, we solve the two problems separately. What's the advantage of separating? Less constant. Okay, so suppose that I concentrate on the even ones. Well, for the even ones, I would say the following. D and A must be the same. Okay? And what about B and C? Okay? B and C must be also the same. Okay, so that this is in fact the cosine of kx times
B.
B. Okay, let's call it B. In fact, I have to put here B over 2 and B over 2 to really get B times the cosine. But apart from a change of name of the quantities, that's the function. Okay, so you see that with this choice, and now only two constants, I have even functions. Okay, now I have to impose conditions. I can impose the condition of the continuity of phi and of the derivative here. Do I need to impose it here as well? No, because the function is even. So if it is continuous with its first derivative here, obviously will be there. So I spare also. So I have two constants, but two conditions. Okay, so a 2 by 2 problem, much easier, right? So I have saved quite a substantial amount of work, and that's general. Symmetry allows to save work. Not necessarily by reducing the problem to something that can be solved exactly, but certainly you save work, even if you just have to rely on a computer calculation at the end. Okay, good. So let's do it. Okay, let's do it. The algebra is rather easy. So I have to impose that the derivative, let's say, for this function, the value of the function at at a minus something, so just immediately before, and the value at a plus something, so just immediately above, are the same. And the same for the derivative. Okay? So what about the condition for the function? Immediately before, I have b times the cosine of ka, right? Immediately after, I have what? A times e to the minus qa. Is this clear to everybody? So these are the two functions calculated infinitesimally before and infinitesimally after x equal a. Good. What about the derivative? Also the derivative have to match. Let's calculate the derivative of this. It is b times k times the sine.
N minus.
With a minus, right, yes. The cosine have this strange thing of giving me minus. Okay, good. And what about the derivative here? Well, the derivative here is, I write it here, minus a q e to the minus qx. Now, let's put it at a. So, I put here a, and I impose that this is equal to minus a q e to the minus q a. Fantastic. Is it clear to everybody? Good. Now these are the two conditions that I have to impose. You might say, oh, they are annoying, right? Cosines, sines, exponentials. This is the typical thing where algebraic solutions are not simple because you mix trigonometric with exponential. They don't mix. It's like oil and water. They don't like each other. But it's nothing dramatic. For instance, suppose that I really don't care about the actual value of a and b. After all, apart from a normalization, what I need is the ratio, right? The overall amount can be changed by normalizing the thing. The ratio is the important thing, right? Okay, so let's calculate the ratio. Well, in fact, it's even better. I have this two equality and this equality and this equality. Let's take, in fact, the ratio of the upper equation divided by the lower equation. Is it clear? This equal to that, and this equal to that. So this divided by that is equal to this divided by that. Is it clear? Of course. Okay, so in particular I take this divided by that. The b goes, and therefore I get k times the tangent of ka is equal to this divided by that. The A goes, and I get Q times the exponential goes as well. Fantastic. Much easier. Okay? Now, you might say, where did the constant go? They disappear. Okay? Will they reappear later? Yes, when I need to normalize and somehow normalize the thing, I have to take care of the constants. But for the time being, I have K and Q only. Well, K, we said, is related to the energy. Let's rewrite it. The energy is just h bar squared, K squared divided by 2m. What about Q? Remember, Q is related to the energy as well, but I have to remember about the V0, okay? So, in fact, let me give you the expression so that I don't get it wrong. Well, we can calculate, right? So, the energy is equal to V0 minus h bar squared Q0 over 2m, okay? So h bar squared Q squared over 2m is equal to V0 minus E, which is positive. So you can take, so in other words, K is equal to 2m, the energy, square root divided by h bar, right? And Q is equal to square root of 2m V0 V0 minus E divided by, let's write it like this. It can be written in many ways. You can take out the h bar. Okay, let's write it like this. These are the K and Q, which appears here. Okay? So, obviously, oil and water. This is not something that you can solve because you see it's trigonometric, but also there are algebraic functions, okay, polynomial and trigonometric. You don't solve it, but we can solve it graphically, and in a second I will show you the solution, okay? But before we do that, let's think of the other possibility, okay? The other possibility is the, or should I first analyze this? What's better? Let's first solve the other, okay? So this is the choice for the even thing. What about the choice for the odd? So phi odd. Let's see how the algebra changes. Here I get A, and here I get minus A. Here I get B, and here I get minus B, in such a way that this is really, apart from i's and things, this becomes B times the sine of Kx. Is it clear to everybody? Okay? By renaming the B's and making the I disappears, I have some constant times the sine. Okay? Again, I need just to impose the condition here, because automatically they are imposed on the other thing. The function is odd, but very clearly related. Okay? So let's see the algebra. The algebra is almost the same. The sine becomes a cosine when you take a derivative. Okay? But here there was a cancellation that I did, because the derivative there brings a minus a e to the minus q a. Okay? Let's see stop me if I say crazy things. You have to stop me. This is the continuity of the function. So b sine k a is equal to a e to the minus q a. Is it clear? Okay, so now let's take the derivative. the derivative of this is b k, the cosine of kx, and the derivative of this is minus a q e to the minus qx. I impose it at the continuity at x equal to a, and I get b k cosine of ka is equal to minus a q
e to the minus
qa. Okay? So let's take the ratio of this divided by that, and I get the b and the b goes, I get k, the cotangent, okay? The cosine divided by sine of ka equal to minus q, okay? So this is the corresponding, so if this is the even case, the odd case is similar. It is k, the cotangent. So in fact, let me write this as follows. The cotangent of Ka equal to minus Q over K. Okay? This is the odd. Is it clear? Very good. Now, what do we do with those things? In fact, let me put the minus sign here. You say, how do I solve it? Well, let's start drawing things. The first thing that I would like to let you observe is the following. Let's calculate Q over K, which is the quantity that appears there. Okay? You see that essentially the 2mh bar square cancels, and you have square root of V0 minus E divided by E. Okay? E is Ek, obviously, the energy. But let me do one thing. I can also rewrite this as square root of V0 over E minus 1. I can write in many ways, as I told you. Let's write this as square root of V0 divided by h bar square k square over 2m. I put the 2m here. Okay?
minus 1.
Minus 1, of course. Fantastic. Then let me just, since k has a dimension, inverse length, and a is a length, let me write this as ka square, and a square, I put it here. Okay? At this point, this is dimensionless, and this also must be dimensionless. Is it clear? Okay. Let's invent a name for this quantity. I call gamma square the ratio between V0 and h bar square divided by 2ma square, which is exactly what you see there, because you can rewrite it as follows. Okay? What is this? Is the ratio between the confinement energy and somehow the kinetic energy, h bar square over 2ma square, the kinetic energy for the particle inside the thing. Order of magnitude, obviously. I don't pretend that this is the exact kinetic energy, but this is the order of magnitude of the kinetic energy confinement, and this is the order of magnitude of the potential energy. Okay? So this is obviously a ratio without dimension, which is the larger, the bigger is V0. A is fixed. Okay? Clear? Good. Obviously you can also rewrite like this. Okay. Good. So this can be written as square root of gamma square divided by Ka square, and now rather than minus 1, I put just same denominator. Okay? Do you agree? One final thing? Yes, why not? Square root of gamma square minus Ka square divided by Ka. Okay? Well, this is useful. Fantastic. This is K over Q. Okay? So I start drawing. Here I put in my axis, not K, I want, somehow you see, Ka is the right variable. You see it appears there. So let's put Ka. The left-hand side here is a tangent. Okay, I will draw the tangent with the white. Okay, let's draw the tangent. The tangent is something like this, right? Where does it diverges? Do you know? Pi over 2. Good. Pi over 2. And here? Minus pi over 2. That's it? No. It's a periodic function, right? So I can have, this is pi, this. The better I draw, the more things are clear, but I'm not infinitely sure that I will be very successful. Okay? So this is 3 pi over 2, and this is pi. And again I have, well, I would have things here, but in the end, I can always take, say, K positive, right? Like you see here is the square root of the 2m energy. So let's ignore what happens, here, okay? So here I would repeat the thing, but let's ignore negative things. Okay, what about, so I'm looking at this thing. This is the tangent. Now I have K over Q. Let's look at it. There is a parameter gamma, depends on the problem you have. So depends in particular on V0. Is the ratio between V0 and the kinetic energy. Okay? You tell me how much. And what is this function? Well, it's just a function that when K goes to 0, diverges. Right? Because this goes to 0 and this goes like 1 over K. And when K goes to exactly Ka goes to gamma, goes to 0. So it's something that could do something like this, for instance. If gamma is very, very small, for instance, less than pi over 2, it would have something like this. Is it clear? Okay? This is this thing for gamma less than pi over 2. Do you agree? It ends with a kind of square root singularity there. If gamma is larger, for instance, suppose that gamma is, I don't know, less than pi, it would be something like this. Okay? If gamma is even larger, it would be something like this. Okay? And so on and so forth. Okay? I don't want to confuse the thing too much. By the way, here there will be an extra branch of the tangents, right? Okay? Something like this, something like this. 5 pi over 2. And this is 2 pi. Okay? Is it clear so far? Hopefully I'm not confusing you too much. Fantastic. So this is the left hand side, the tangents, okay? And the right hand side depends on the value of gamma that you choose. Suppose that I have chosen the smallest value. How many solutions do you have? One. Here it is. Okay? There is an even state in the problem. And you see that there is nothing you can do. Even if you take V0 very, very, very small, a minute step, like this. Okay? Gamma is very, 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 very small, and you do something like this. There. you have your ground state. There is always a bound state, no matter how small the step is. That's kind of amazing, right? Good. So you have only one. What about, for instance, this situation here? I have two solutions, two even solutions. We will see now in a second that there are also odd solutions, okay? What about, well, here I still have two, but suppose that I have something like this. Okay, I would have three even solutions. Okay, 1, 2, and 3. Good. How do we find it? Numerically. Okay, just use your preferred zero finding routine. Okay, use Python. What do you use to do numerics? Fortran. Okay, in Fortran there are Fortran quotation marks. Okay. You will learn, I think. Marcello Del Monte will or maybe others. I don't know. Mauro Solito. I don't know. I think you will do some numerical.
Yeah, we are.
You are already. Okay. So root finding. Okay, finding roots of equations. No linear.
Against our will.
Huh?
We are learning Fortran against our will.
Yeah, it is a reasonable thing. Although, I mean, you should learn numerics not against your will, because it's a very important tool, even if you want to be a purely theoretical physicist, because you always need to do some numerics, no matter what you do. I mean, being a clean pen and paper person is extremely rare, okay? So do the numerics. Fortran is a little bit on the old side. Now there are much more kind of modern things like Python, okay? And I would encourage you also to get a little bit modern as well. So don't stick to Fortran for the rest of your life, because the world goes on and things happen. There are things like Python, for instance, that lets you do lots of things easily, okay? Which you can do always in Fortran, obviously, but it's much more clumsy. There are applications where Fortran is unsurpassable because it's faster than, okay? So, in some sense, both are useful. Okay, let's stop the blah blah. Let's write the cotangent, okay? Now, it takes just a little bit of reminiscence of trigonometry to remember that minus the cotangent is this function. Okay, so it looks like the tangent but shifted a little bit by pi over 2. That's it. And this also. Okay. Beautiful. Huh? So, in some sense, the minus the cotangent diverges at pi, at 2 pi, and so on, and it has zeros at this half integer pi's. Okay? Good. Now let's look at the situation I depicted here. How many solutions total you have? 1. Only the even. You see that the odd is not possible. What about here? 1 even and 1 odd. Okay? What about, say, here? 1 even, 1 odd, 2 even, and 1 odd. Okay? So by increasing gamma, I start increasing the number of bound states that I have. From the absolute minimum, which is always there, 1 bound state even, 2, 1, 1, 1, 1, the other. Okay? And so on and so forth. For instance, in the situation depicted here, I would have 1, 2, 3, 4, 5. And in the situation here, 1, 2, 3, and 4. Okay? In fact, counting the states is not difficult because somehow this is, remember, the value of gamma. Okay? At this point, gamma is exactly equal to Ka. Right? So if I tell you, suppose that gamma is 5, gamma equal to 5, you might say, well, 5 is less than 2 pi, but greater than 3 pi over 2. Is this right? Yes, I think it's right. It is. No, it is. So, gamma equal 5 might be the curve that I'm pointing it now. Okay? So you would have 1, 2, 3, 4 total solution, 2 even and 2 odd. Now, here they are. Okay? Ground state, first excited state, second excited state, third excited state. Even, odd, odd. Notice, this looks like, remember our infinite well calculation. The ground state was this. Okay? Which was seen in the first attempt as a sine. But then we realized that if we put things in the middle, it's a cosine. It's almost the same, except that now the function is not really going to 0. It's going to something and then have a tail. The tail is this. Okay? So it's like a cosine but spreading a little bit outside. Why? Because now this is not infinite, so you can a little bit visit the forbidden region. Okay? In the infinite square well case, there was no possibility. And therefore this... So you see here, the derivative is still smooth. When you go to here, the derivative is finite here and 0 here. So there is a kink, right? So, is it clear? Good. So these are the functions. They all have... So this is the sine function now, which is spreading. This is the cosine with 2 oscillations, spreading. This is the sine with 1 more oscillation, spreading. Okay? Clear? Good. What do I want to tell you? Okay. Very good. Yes, just this thing about the number of bound states that you have. Remember, if you have a gamma that is between NB times pi over 2, okay, and NB minus 1 pi over 2, okay, then you have NB bound states. For instance, in this case, this was between 4, because this is 2 pi. Okay, so that's a formula, little formula. You give me gamma, I look for the number such that I bracket it between pi over 2 and pi over 2 minus 1, and that's it. The number is easy to count. How, what is the actual solution? Fortran or Python or whatever, root finding. You find the values. By the way, just let's see what happens if you send V0 to infinity. Okay? What happens to all this picture? Gamma becomes infinite. Ah, very nice. But if gamma becomes infinite, what is this curve? Something flying down up there. Even more. Second floor, third floor, infinite floor. Okay? So where does you find the points? Ah, there. Yes. Exactly. Okay? So you put the value of k equal to pi over 2 pi, 3 pi over 2. And what do you get for these energies? The energies that we calculated, remember, in the first attempt of our infinite square well. Precisely. Okay? Because if pi becomes, remember in that case, I had that k was n times pi over l. Remember that a is equal to, l is equal to 2a. Okay? So somehow k times a is equal to a multiple of pi over 2, which is exactly what you have there. Okay? So obviously in the limit in which V0 goes to infinity, you recover the solution you had before. Clear so far? Okay. In the notes, I ask you to calculate the problem of scattering from from the same. The figures in the notes are not always, because I just cut them from textbooks, so they should be slightly adapted in some sense. Maybe I will do that before. So, for instance, problem 2.6 asks you to do exactly in this problem here to calculate the scattering solution. Okay? So I have now an energy here, and I want to calculate the scattering solution. Okay? So what do? You say, I have region 1, where my function will be e to the I kx plus rk e to the minus ikx. Okay? I have region 2. Sorry. Okay, let's put things properly. Let's use here the q. Okay? Because again, the k here and the q here are different, and they differ by this v0. Since I'm putting the zero of energy here, I will use q for this region. Okay? What about the wave function here? It's a combination of plane waves with e to the ikx. Okay? Forget about the symbols that I use there, which might confuse you a little bit. Let me call the wave function here a e to the ikx plus b e to the minus ikx. What about the wave function here? Let's use the usual trick. Just, tk, yes. E to the iqx. I just impose it that is a running wave with the same wave vector as here, but without the other term. I can always, obviously, take the star, make a combination, and blah, 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 ask for the single step. But this saves me a lot of calculations. Because now, remember, that I have this to determine, this to determine, and this and this. 4 conditions. And I have to impose 4 conditions on continuity, continuity, derivative, and derivative. I'm not using, by the way, parity here, because I'm setting this in a scattering geometry, okay? Which makes me save work as well, okay? So while for the bound state I explicitly use the parity, here I don't use the parity, but I use the scattering geometry, which makes the problem easier. And here you have your problem. So 4 unknowns and 4 conditions to impose. Please. This is the exercise 2.6. Okay, so if you want, just I remind you that figure 2.4 is taken from a book where the zero of energy was here, and now I'm asking you, please put it here. Okay? So just amend a little bit the figure. Good. What else? I'm going slow. There are a series of other exercises. For instance, a closely connected exercise is, suppose that I ask you for this problem here. Okay? Now the zero of energy here, this is minus A, this is A, okay? And this is V0, positive. Okay? Now again, I have a scattering problem. Here, E could be less than V0 or greater than V0. Okay? Try to see what the problem asks you. 2 points, this is problem 2.7. And then I have some other things. 2.8 is, for instance, doing this. So here it is infinite, and here it is, this is 0, and this is A. Okay? And this is V0. This is exercise 2.8. Ignore 2.9. It's a stupid repetition, I think, of this. Okay? For some reason I have a... Read it if you want, and you will see that it's just a shift of the zero of energy. So obviously, all the calculations done before can be... More complicated problem is 2.10, is the transmission in one dimension, where you learn a little bit more about this story about taking the star, combining things. So this is definitely the most complicated problem in this section. Okay? Now, before we end the discussion, let's do one more things that can be done. It is the following problem. It is the problem of the delta function. Now, the delta is a very singular object, right? And in some sense you might say, what do I need to care about? Because in many problems you have very narrow attracting potential which are however strong. In some sense you can see an attractive delta function in the following way. Suppose that I have a well, okay, between minus a, and some, say, depth minus b0, and I make it smaller and smaller, but by making it deeper and deeper, in such a way that the area of the corresponding rectangles are the same. Okay? So the ratio between, the area 2a times v is the same in the okay, in the limit in which a goes to 0, obviously the potential is always 0 everywhere except for a delta function, okay, at 0 somehow. Because remember that the integral of a delta function is just 1, no matter 1. It depends on the coefficient in front, okay? No matter how close you go to the 0, okay? So, my suggestion is let's try to see what happens if the potential V of x is equal to minus, so it's negative, some constant V0 times the delta of x, the Dirac delta. Okay? Don't think that V0 is an energy, because the Dirac delta have a dimension. Remember? Because if I do the integral in dx of the delta of x times some function of x, I find f of 0, right? So whatever the dimension of this f is, this object should have no dimension, which means that the physical dimension of the delta is 1 over the length. Okay? So don't be mistake. So this is not an energy, but the energy times length. Energy times length. Okay? In such a way that you multiply by the delta and the result is an energy. Okay. You clear? Good. So this is my problem. Now I want to solve for the bound states. Okay? So I draw the potential. The potential is some singular thing there. X, 0. Okay? I could do energy, so the minimum of the potential is minus infinity. So anywhere I could have solutions. And in fact, for E greater than 0, I will have scattering solutions. But what about E negative? Can I have somewhere a bound state? That's the question. Okay? Or more than one bound state. We'll see there is only one. How do we determine it? Okay. I do not erase this because it would be useful in a while. Okay. First of all, what would be the possible form of the wave function here for x less than 0? The potential here is 0, but I want some energy E that is negative. How do you get negative energies in limited region of space when the potential is 0? Decaying exponential, the usual object, right? So A e to the q x. Okay? What about A e to the minus q x? Okay? You might say, why did you select the same A? This is an even function. Okay? A function that, if I draw it, does like this. Notice it has a discontinuity in 0. Okay? But we'll see. Let's start looking at even functions. In a second, I will show you that there is only one bound state, and therefore this must be even. There are no possibilities of odd. By the way, an odd function is 0 in the origin, so it doesn't feel the delta in some sense, and therefore, obviously, it's not bound by the potential, because if you don't feel the potential, it will not convince you to be bound. So certainly the function should be even. But we will see, there is only one, so whatever we do is correct. Good, fantastic. We still, okay, what about Q? How is Q related to the energy? Remember, the energy is negative, it is minus h bar square, Q square divided by 2m. Okay? All Q's are possible, so all energies are possible? No. There will be a special Q, and therefore a special energy, which solves the Schrödinger problem. How do I set it up? I set that up in the following way. I should have minus h bar square over 2m, the second derivative of the function, okay, equal to what? Equal to E minus the potential times the function. Remember, I can always bring the potential to the right. And in fact, we did exactly this type of exercise when I showed to you that the first derivative is continuous. Okay? Now, I don't pretend this, but I can always integrate between, say, minus epsilon and plus epsilon. Okay? What is the integral of the left-hand side? It is equal to the first derivative calculated in epsilon minus the first derivative calculated in minus epsilon. Okay? So what is the integral of the right-hand side? Well, it is the integral of E times phi of x between minus epsilon and epsilon minus, well, the potential is, so it's plus V0, the integral of the delta function of x times phi of x. Is it clear? How much is this? V0 times phi calculated in the origin. The function must be continuous, obviously, so there is a uniquely defined f0, which is in fact here equal to a. Okay? Phi of 0 is equal to a. Very good. Now take the limit epsilon going to 0 of this and of this. Okay? How much is this? Is the integral of this little thing when you shrink the thing to 0. So this goes to 0 in the limit epsilon goes to 0. And this is what? Is minus h bar square over 2m. The derivative calculated in 0 plus minus the derivative calculated in 0 minus. So slightly after and slightly before. Okay? So I have obtained a condition that I have to satisfy, which is the following. Is it so far clear to everybody? So I did a little bit of the ideas behind the proof of the continuity of phi prime that we did last time. But now I do not conclude continuity. In fact, due to the fact that the v is not just a step, but is a delta, the function is not continuous. Okay? So here I have a derivative, and here I have a different derivative. But the difference between these two derivatives, apart from h bars and m, is related to the strength of the potential. Okay? So let's calculate what you have there. So if this is the phi of x on the left and the phi of x on the right, let's calculate this. So phi prime of x is equal to minus a e to the minus qx. Now what about the phi prime here? A, so phi prime, a q e to the qx. Okay? Good. So I have minus h bar squared over 2n. The derivative in 0 but plus. Okay? So I use this expression and I put 0 here. So it's minus a times 1. Okay? Minus the derivative in 0 but minus, so I have to use this. Okay? So I put 0, this becomes 1, minus a, sorry, there was a q. Minus a q. Okay. This should be equal to v0 times the function in 0, which is just a. Okay? So the minus and the minus in fact go. And the a is a common factor, I put it here. And this is just 2q. Sorry, I used the blackboard in a substantial way. Okay? Now you see that a is not really important. It goes. But I have finally obtained my required condition, which is that h bar squared over 2n, over n times q is equal to v0. And notice that it's not q squared, so v0 is not an energy. As promised, v0 is energy times length. Okay? Very good. Once you give me this, I could calculate E. Okay? So I could calculate from here Q equal to m v0 divided by h bar squared. And therefore the energy here E equals, so the bound state energy equal to minus h bar squared, the square of this, divided by 2m. So m squared v0 squared divided by h bar to the 4th power. Okay? So this and this goes, and this becomes minus m v0 squared divided by twice h bar squared. Okay? If you put the dimensions, this is an energy. Okay? So it's the negative energy bound state of this problem, and the function is somehow. So what is this? Look at this function here. Imagine that you set a to 0 and you do the trick that I did before. The cosine in the middle disappears, and the only thing that is left is the two exponential waves. Okay? So that's it. Now, you might say, how can I be sure that this is the only one? Well, look at gamma. Now, here, what is the small v0? Small v0 is the integral of this thing, right? Because the integral of minus v0 times the delta of x, okay, is minus v0. And on the other hand, for this square discretization, the integral is equal to minus 2a times big V0. Okay? So you see that there is a relationship between big V0a and V0, which is the following. A times V0 times 2 is equal to small v0. Okay? And the prescription is send a to 0, v0 to infinity, so this to 0, V0 to infinity by leaving the product constant and equal to V0. Okay? That's the prescription for going from this square wealth to the Dirac delta. Okay, let's do that. So I write this as A times V0 times A. Okay? And there is even the 2 if you want. So 2A V0, this object here, is my small V0. But there is an extra A. Okay? So what happens? Gamma goes to 0. Okay? So in the limit in which you try to get the Dirac delta, so you take A going to 0, you get gamma going to 0. But gamma going to 0 is exactly the thing that I was describing before. Okay? So you're going to 0. And if you do the proper limit of everything, you will realize that indeed you get the solution we got. There is no other solution, because there is no possibility of intercepting anything else in your solution. Okay? Okay, that's it. I think we should end up here. So next time we start with harmonic oscillators. Okay? So we move towards more. So after the harmonic oscillator, we will do a little bit of pause for setting up a more general theory of quantum mechanics. So far we have worked with the wave function. It will be a little bit more general and a little bit more abstract, introducing the concept of cats, of Hilbert spaces in a slightly more refined way. And then we will proceed, hydrogen atom, angular momentum, and so on and so forth. Okay.